right, welcome back everybody. In this video, we're continuing with section 4.5 with exponential and logarithmic equations. And in this video, we'll be focusing on applications. So the story for this one is it says that Nancy wants to invest $4,000 in savings certificates that bear an interest rate of 9.75% per year, which is awesome, compounded semi-annually. We want to know how long a time period should she choose if she wants to save an amount of $5,000. So she's putting 4,000 in and she wants to get 5,000 out. So how long is it going to take? So we had a compound interest formula that went like this. And in it, the P was the principal or amount invested. The R was the interest rate as a decimal. The A was the future amount. The T is the time, and N is the number of compounding periods per time unit, which is usually years. And so in the past, we basically solved for either A or P. Now that we had no more, we're able to solve for T. We still are not able to solve for N because that occurs in two places, which presents a lot of complications, but we can solve for T. And fortunately, that's a common question. So let's put in the information we have and then see about solving for T, because the answer is how long a time period should she use. So that means we're solving for T. All right, so let's go ahead and put in what we know. So she wants to end up with the 5,000. And she's starting with 4,000. 1 plus her interest rate is 9.75% per year, so that's 0.0975, is compounded semi-annually, and that's 2 times a year. Make sure you know the difference between semi-annually and biannually. Biannually would be every 2 years. Semi-annually is every half year. Okay, and so that's going to be N is 2, and then T is again our variable. So this time we're solving for T. And so as we know, how to get access to an exponent is by taking logarithms of both sides. Before we do that though, I'm going to try to do a little simplification. I'm going to divide both sides by 4,000 first. So that will give us 1.25 on the left side. And then here inside parentheses, let me go ahead and work out what that decimal is. And if you don't feel like doing that now, you can hold off on it till later. Okay, so now that's 1.04875 raised to the 2t power. So now, once again, we're going to take the logarithm of both sides. And again, it's up to you which one you choose. In the past, people usually use common logs just for variety's sake. I'm going to use the natural log this time. So let's say natural log 1.25 is equal to natural log 1.04875 raised to the 2t power. And again, and as always, our reason for doing that is so that we can bring that exponent around front. So that you'll see that 2t moving around front here in the next step. Natural log 1.25 is 2t natural log this decimal. And then finally, we want the t by itself. So we're going to divide both sides by the 2 natural log 1.04875. Okay. And so that's what's going to make it so that our t is all alone on the one side. So we'll have natural log 1.25 over 2 natural log 1.04875. That will be our t. So let's go ahead and get a decimal approximation for that. Be really careful how you type this into the calculator, especially with that 2 in the denominator. Make sure that if you've done it as I have, that you use the natural log. Definitely do not mix the two kinds of logarithms. All right, so I'm getting like 2.34 years. Okay, so there's our first example of how you can use logarithms to help you solve a story problem. All right, so this example is a lot like the last one, only the compounding is done continuously rather than by uh, semi-annually. So, all right, so as you recall, the formula for continuous compounding is A is equal to P e raised to the RT power. And so again, let's substitute in what we have and see what we know. So it says, how long would an investment take to double if it is invested at R% compounded continuously? So on this one, there's no real numbers, right? It says that our investment is supposed to double from whatever it is to begin with, and the interest is just R%. So what can we do? Well, the principal amount is just P. If it's going to double, it will turn into 2P, right, after time T. And so we can divide out the P's on both sides. P is non-zero. If it is zero, it's never going to double, so forget that. You can assume that P is non-zero. So then 2 is equal to e raised to the RT power. And then this is basically just R and T are the two variables here, and we want to solve for T as a function of R. So we'll take the natural logarithm of both sides. Here again, once again, I'm using the natural log because the problem has an e in it. So we'll have natural log 2 equals RT natural log e. The natural logarithm of e is just 1. Natural log 2 is equal to r times t. So solving for t will be natural log 2 over r. And that's kind of neat. Natural log 2 is a constant, right? It's about 0.69. And so the time is actually a rational function of the rate, right? So this looks kind of like the reciprocal function if you graph it. Which makes sense. As time increases, or as the rate increases, the amount of time it takes to double will decrease. If you have any kind of a business background, by the way, and you've heard of something called the rule of 72, okay, what the rule of 72 is about basically is that you can, in order to find out how long it would take an investment to double, you divide the interest rate into 72. For example, if you had a 9% interest rate, then your investment would double in 8 years because 9 goes into 72 8 times. The reason why it's called that is because 72 has a lot of factors, which is good. But where the rule comes from basically is this ln2 over r formula. And so the problem, though, or the thing is that the natural log 2 is about 0.693 and change. So they call it the rule of 72 instead of maybe the rule of 69. Okay. All right, last example. So here it says the half-life of strontium-90, that's some radioactive stuff. The half-life of strontium-90 is 28 years. We want to know how long it'll take a 50 milligram sample to decay to a mass of 32 milligrams. So that sounds kind of complicated. I'll take a few minutes to read that over and see about how you might set that up, and then we'll work through it together. All right, so there's a variety of ways of approaching this. This seems probably the most straightforward. I remember that our kind of basic formula for an exponential function from our first day looks like this. F of x is ab to the x, and b is our related to our growth rate, and a is the initial value, right? F of 0 would equal a, so that's like the initial amount. And so we're going to use this. So here it says the half-life of strontium-90 is 28 years. So that's kind of the background information. And then the second sentence is the question. So I have to be able to figure out the function that I need based on this first sentence. So the half-life, what half-life is the amount of time it takes for half of a radioactive substance to decay into something else. And so whatever it is, however much you start off with, b raised to the 28 years. If we let it sit for 28 years, it's in a decay into half of a. Okay, so that's what the half-life means. Okay, whatever amount you start with, call it a. If 28 years goes by, you'll end up with half that a. Okay, so again, just as in our previous example, we're going to divide out the a's. There, of course, have to be non-zero, but if there's zero of it in the first place, then the question is kind of dumb. Okay, so we have 1/2 is equal to b raised to the 28th power. So this time, this is kind of interesting because our unknown, our variable is in the base, not the exponent. So we don't really need to do logarithms here, although we could. We could take the 28th root of both sides. That's probably going to be easiest. So yeah, so let's do that. Maybe we can do this in two ways. That'll be fun. So we're going to take the 28th root of both sides. So we'll take 1/2, which is equal to b to the 28th power. And we're going to raise it to the 1/28 power. Okay. All right, so then we can get a decimal for the right side there. Our b will be 1/2, that's 0.5 raised to the power of 1/28. And that's about 0.97555. Okay, it's less than 1, which makes sense because it's decreasing, right? And so that's going to be our b. Okay, so now we want to know how long it's going to take a 50 milligram sample to decay to a mass of 32 milligrams. So we're going to start with a 50 milligram mass. Our base is 0.97555. It's going to be raised to the t power. We don't know how long it's going to take to drop down to 32 milligrams. Okay, so now we're ready to solve for t. So before I take logs of both sides, I'm going to divide both sides by 50. So we'll have 32/50 is equal to this decimal again, raised to the t power. 32/50 is 0.64. Okay, now we're ready to take the logs of both sides. This time, just for fun, we can use the common logarithm. So let's do that. So we'll say log 0.64. I forgot the t. And that will be log 0.97555. And that was raised to the t power. Okay, again, our reason for doing that is so that we can bring that t around front. So we have log 0.64 equals t log 0.97555. Okay, dividing by the log of 0.64 on both sides, we'll have log 0.97555 divided by log 0.64. Okay, and that's about 0.055. Okay. That seems small, so I'm kind of checking my work. All right, so I wasn't expecting it to be 1/20th of a year, right? A little more than 1/20th of a year. So let's check and make sure that that makes sense. Yep, it looks like it checks out. 50 milligrams will decay to 25 milligrams in 28 years. So to go down to 32 milligrams, that seems really fast. So let me double check my work. All right, so I just forgot algebra for a minute. So this is exactly upside down. We need to have t as log 0.64 divided by log 0.97555. So sorry about that. It seemed too small. All right, so 18.03. And that's going to be in years. Yeah, all right, that's much more like it. All right, so sorry about that. So that's better now. So the way that we had found the b before was by taking a 28th root, and we're done now. But I wanted to show how we could have done this using logarithms instead. So let me take it from here. And so we had 1/2 is equal to b to the 28th power. We want to solve for b. So we're going to take the logarithm of both sides. And so log log is fine. So we'll have the common logarithm of 1/2. That was 0.5. And that is log of b raised to the 28th power. And then our reason, as always, for doing this is to bring the 28 around front. So we'll have log 0.5 is equal to 28 log b. Okay, so now this is a log equation that we can solve. So this will be log 0.5 divided by 28, and that will equal log b. Okay, and so now this is a logarithm equal to a number. I know this looks complicated, but it's log 0.5 divided by 28. That's just a number. And that's log b. In fact, let me just calculate what that is on that other side. That's log 0.5 divided by 28. That's negative 0.01751. And that's our log b. So 10 raised to the power of negative 0.01751, that will be our b. Okay, and here I'm getting 0.9604. And that is because I rounded so much in here. So the b that we calculated before was not 0.97555. Because I rounded in here twice, it ended up off by a little bit. But that's the procedure that you could follow rather than taking the 28th root. All right, so that finishes up this section for us. Let me know if you have any questions, and have a great day.